down and I'd like to have the floor to those.
あったんですよね、ネットで10ドルぐらいで買えるやつ。ここのじゃないんですけど、金で買うからちょっといいかな。そうなんですね。あんまりなんですね。ショットガンもちょっと短いし。
Okay, thank you very much. So, ladies and gentlemen, the next chapter in the medical physiology is the circulatory system, and at the very beginning is the heart physiology. The heart is very important in maintaining the circulatory system. Now, first we have to speak a little bit about the anatomy of the heart. In the human body, there are two circulatory systems. The first one is the pulmonary circulation, and the second one is the general circulation. Now, the circulation is maintained, the circulation of the blood is maintained by the heart. The blood arrives to the right side of the heart, into the right atrium, and through the atrioventricular layers, it arrives to the right atrium, and from this right atrium, the contraction, the systole, forward the blood into the pulmonary circulation. The blood arriving to the lung will take up the oxygen and will release the carbon dioxide. This is the role of the lung in the circulatory system. Now the fresh blood, full of oxygen, without carbon dioxide, will arrive back to the left atrium, and from the left atrium into the left ventricle. The contraction of the left ventricle will forward the blood into the general circulatory system in the whole human body, supplying the different cells and tissues by oxygen and taking up the carbon dioxide. Therefore, the heart has a right side and has a left side. What is the middle difference between the two circulatory systems? The biggest system is the intra-arterial pressure. The arterial pressure in the general circulation is roughly 120 millimeter mercury. It's relatively high pressure because this pressure maintains the movement of the blood into the whole circulatory system. The right side, the pulmonary circulation, is a more simple one. Therefore, it doesn't need so high pressure. Therefore, this pressure is roughly 20-30 millimeter mercury also. Therefore, the right ventricle has a smaller mass of muscle. The left ventricle has a much larger volume of the muscle. You have to know that the cardiac output of the left side and the right side has to be equal all the time. Now, speaking about the cardiac physiology, we have to see first how the action potentials are generated, because the cardiac muscle cells excitable cells, and they need the action potential for the contractile response. First, we will speak about how the action potentials are generated. After, we will speak about how the action potentials can evoke the contractile response it is the so-called excitation, contraction, coupling. How do you learn it from the skeletal muscle? Now, and the third part of the cardiac physiology, that if the heart contracts and relaxes, there is a systole and there is a diastole. Now the question is how the pumping activity of the heart is able to maintain the circulation in both circulatory systems. Now first we have to speak about the electrical properties, the impulse generation and the conducting of the action potentials. You have to know if we remove the heart from the human body, the beating of the heart will be continued for a long time. It clearly indicates that the pulse generation, the action potential generation, is an inherent properties of several cardiac muscle cells. The action potentials are generated within the heart and they don't require any external stimulus. So the impulse generation is an important property of the heart. And the generated action potentials has to propagate to the whole heart to be able to do a complete contraction. Now, therefore, we have to speak about the generation of action potentials and the action potentials which can be recorded from the working cardiac muscle fibers. Now, the best way to study the electric properties of the heart is to record the action potentials and different parts of the system. The sinoatrial node located at the right atrium, the wall of the right atrium, sinoatrial node, it is the most important pacemaker center of the heart. The place of the impulse generation. This action potentials propagates along the atrial wall, cardiac muscle cells. They reach the atrioventricular node and propagate further to the ventricular muscle fibers. Now, if we record the action potentials, you can see that there are very severe differences what we can record as the SA node or the AV node, and those originates from the atrial So there is a significant difference in the shape of the action potential at the SA node, which is the basic pacemaker cells, and the ventricular muscle fibers. What are these differences? There is a difference in the latency time. It is much longer, it is shorter. The time course. These are fast action potentials, and these are fast action potentials. Time course. The resting potential is different. You can see that the SA node has a membrane potential at minus 60 millivolts. The ventricular muscle fibers has a resting membrane potential minus 90, much more hyperpolarized. And there is a significant difference in the amplitude also, because this is a smaller amplitude and this is a larger amplitude. Now, summarizing this whole business, we can record different shape of action potentials with different parameters, kinetic parameters, voltage dependence, and so on. Electric activity from the SA node is very similar to the AV node, has the so-called pacemaker potential. This is the slow response. And the atrial muscle fiber, the ventricular muscle fibers, and the Purkinje fibers, they have the so-called fast response. The time course is much faster, amplitude is larger. Now the question is, what is the ionic mechanism of the pacemaker activity? And what are the most important properties of the action potentials in the working muscle fibers, which are responsible for the contractile response? Now let's go we can study first the slow response, which is the pacemaker potential. These are typical pacemaker action potentials. The most negative membrane potential value, as we mentioned, is minus 60 millivolt Kelvin. There is a slow rising phase, and later there is a little bit faster rising phase, but not too fast. So, therefore, if we try to analyze the pacemaker activity, we can speak about the low resting potential, the most negative value. And this is because this membrane is leaky for the sodium ions. So the resting sodium permeability is not so small than in the neural structure or the skeletal muscles, but the sodium activity is a little bit higher. Therefore, the sodium permeability results in less negative resting potential. And the other important feature of the membrane is that we do not find fast, voltage-dependent sodium channels which are responsible for the very fast action potentials on neural structures and on the skeletal muscle membrane. Okay, so this is what is the reason that so low is this membrane potential. The next part is the diastolic depolarization from the most negative value up to the beginning of a little bit faster rising phase. This slow depolarization, diastolic depolarization, because in time this depolarization coincides with the diastole of the muscle membrane. Okay, and after a faster action potential appears, and this is the pacemaker action potential. What is characteristic to the pacemaker action potential? There is a slow rising phase. It is slow because the depolarization is resulted in by the increase of calcium conductance, calcium permeability, the opening of calcium channels. And because these channels have slower kinetics comparing to the fast sodium channels, therefore the rising phase is slower. Okay, what is the reason of depolarization? Similarly, that the calcium ions, calcium channels will close, and the potassium channels will open, and they will result into the repolarization. So this is the slow action potential. What is the role of the diastolic depolarization? The second video. The diastolic depolarization slowly depolarize the membrane because the sodium and calcium channels can enter through the resting membrane. And there is a hyperpolarizing effect of the potassium. Therefore, the potassium current decreases, the calcium current increases, therefore, there is a slow depolarizing phase. What is the significance of this slow depolarization? It's very important because this depolarization opens the calcium channel, which bring about the rising phase of the pacemaker action potentials. The other very important significance of this period, this will determine that how long is the interval time between two pacemaker action potentials. In other words, how high the heart rate will be. If this period is short, the heart rate is high because more action potentials can fit to the 1 second or 1 minute interval. If this diastolic depolarization is longer, in this case the heart rate will be lower. The lower heart rate is the bradycardia. The faster heart rate is tachycardia. Do you know, the normal heart rate in the human persons is 60, 70 over a minute. If the heart rate is lower than 60, we can speak about bradycardia. And if the frequency is higher than 70, we can speak tachycardia. Now the question is, how the duration of this diastolic depolarization can change? Can be longer or can be shorter? There are 3 different possibilities, but generally all of them will happen at the same time. What can result in the change in the duration of diastolic depolarization? It is the autonomic nervous system, the sympathetic fibers, activity of the sympathetic fibers, the adrenergic stimulation, and the activity of the parasympathetic fibers, the cholinergic innervation, will result in bradycardia. Okay, what is the first statement? The heart itself cannot change the heart rate. The heart rate is exactly determined by the ionic properties of the pacemaker cells. The heart cannot modify it. How the heart rate can be modified? By the autonomic nervous system, by the adrenergic or cholinergic innervation. Okay, how these transmitter substances, epinephrine, acetylcholine, can increase or decrease the duration of this diastolic depolarization. The first possibility, then the slope of the diastolic depolarization change. If the slope is steeper, in this case, it will reach earlier the threshold potential of the calcium channels. If the rising pace is slow, not so fast, it takes longer time to open the calcium channels. The other possibility is the value of diastolic repolarization, the more negative value. In this case, if this diastolic depolarization is a more negative value, the diastolic depolarization will start from here and takes longer time to reach the opening of the calcium channels with the same steepness. But on the other hand, the threshold of the opening of the calcium channels can change also. If it is more negative, if you reach earlier, if more positive, it takes longer time to reach it. So therefore, the slope of the depolarization, the starting point or the opening of the calcium channel can change, the voltage dependence can change. Therefore, this modification will result in the change in the heart rate. Now, we mentioned that the bradycardia is caused by the cholinergic innervation. This figure shows that the stimulus of vagal nerve will slow down the heart rate, and we finish the stimulation. Slowly the acetylcholine source release will be hydrolyzed by the acetylcholinesterase enzyme. The effect of vagal stimulation will disappear, and the heart rate will be again at the starting heart rate force. We mentioned at the same time of slow action potentials can be recorded in the SA node or in the AV node, because both places contain pacemaker cells, cells which are able to generate action potentials. Therefore, there are many places in the heart where pacemaker activity can appear. First possibility is the activity of the SA node. This is the normal pacemaker place of the human heart. The generated frequency is 70, 80 over a minute. We mentioned that the normal heart rate is generally 60, 70, a little bit lower. It is due to the vagal nerve activity, as discussed a little bit. But there are pacemaker cells at the AV node. The characteristic feature of the cell that they can generate action potentials only at lower rate. They can generate pacemaker action potentials only 40, 60 over a minute. And finally, we can find different pacemaker cells in the Purkinje fibers, which are neuronal structures, and the Purkinje fibers can generate action potentials only 20, 40 times over a minute. Therefore, this is the slowest place where action potentials can be generated. Okay, so summarizing, we can say that the impulse generation in the human heart can be at the SA node, which is the most important physiological pacemaker center. Therefore, we used to call it nomotopic pacemaker center, because these nomotopic cells are responsible in most cases for the heart rate. The ectopic pacemaker cells, which are located in unusual places, they are heterotopic pacemaker cells, are slower. Therefore, we can translate the whole nomenclature saying that the SA node is a primary pacemaker, AV node is a secondary pacemaker, and the Purkinje fibers has pacemaker cells which belong to the third pacemaker center. Now, summarizing, different cells are able to generate action potential, but the normal activity of the heart requires that only one place will generate the action potentials, because those cells which are generate the pacemaker at abnormal time and abnormal places will result in cardiac arrhythmias, will result in extrasystoles or fibrillation. Therefore, there is a mechanism in the human heart which is important, that only the SA node will be responsible for the heart rate, and the AV node and the Purkinje cells will be silent and cannot be active in normal circumstances. Why cannot be active? This figure clearly indicates that it is the pacemaker activity of the SA node. It is the dominant pacemaker or the physiological pacemaker. And when these action potentials are generated, they will propagate it and will reach the AV node. The AV node, because it has pacemaker activity also, started to generate its own pacemaker action potential. You can see here the diastolic depolarization. But it's quite sure that the circumstances makes possible that a longer time is necessary to threshold of the voltage-dependent action potentials, or here is the slow response, a longer time. But this time is too long, and the action potential from the SA node arrives earlier here than its own action potential can be generated. Therefore, the subordinate pacemaker is too slow, too lazy to be able to generate action potentials. Therefore, they remain subthreshold, and the evoked action potential will appear earlier. Okay, but there are cases this mechanism doesn't work, and different extrasystoles or fibrillation can occur. Too much action potential generation happens at the same time, and these are called cardiac arrhythmias. The cardiac arrhythmias is a very important chapter in the cardiology, because you know the sudden death cases, many occasions is due to the heart failure and the abnormal activity of the heart. This type of abnormal activity is the extrasystole and the fibrillation. We have to speak about the mechanism of these pathological cases. These belong to the active cardiac arrhythmias. The other group is the passive, when everything is suppressed and the impulse generation or the transmission of the impulses is blocked and cannot cross to the AV node. It means that the ventricle will not get the action potential, and maybe the ventricle will stop. It's not necessary to speak about it now because it's a longer story. But the active arrhythmias, the extrasystoles appear for fibrillation zeros. It can be due to different reasons. The first simple reasons that the silent pacemaker starts to be active and generate action potentials, extrasystoles. It means that the SA node generates the pacemaker action potentials by a frequency of 70 over a minute, but its reactivated AV node generates 10 more action potentials during a minute. Therefore, these 10 action potentials will appear in the heart membrane, in the cardiac membrane, as an extra action potential, evoking extra systole. The other possibility is the heart surface is not homogeneous. In normal case, the action potentials arise to the heart and to the ventricle. The whole ventricle will be repolarized, and after the whole surface will be repolarized and will be able to accept the next action potential, the next cardiac cycle. But if the repolarization after the repolarization is not homogeneous, it can occur that a certain area of the ventricular surface remains repolarized and the other areas will completely repolarize orderly. What the repolarized part, how they will behave, what they will do, they work as an excitation part. And a similar thing when we apply microelectrode and stimulate the membrane and we evoke action potential. Now this repolarized segment can evoke action potential and can cause extra systoles. Now in this action potential generation from the repolarized area has a high frequency, in this case fibrillation will develop. What does it mean, that fibrillation? Fibrillation means that the frequency is very high, very high. When the atrium fibrillates, you see that the frequency is 220, 350 over a minute. Very high frequency. And the ECG report, you cannot differentiate the T waves. There are many, many T waves. But the fibrillation will not reach the atrium. But there are ventricular fibrillation, and the atrial fibrillation will appear in the atrium, and many, many action potentials will appear, and the membrane potential simply just oscillate. There is no normal repolarization part. Okay. The third possibility, when the extra action potentials are generated, is the so-called re-entry mechanism. This re-entry mechanism is a relatively new thing, a new discovery, and this re-entry mechanism can explain many times the arrhythmic alterations. Okay, how the normal cardiac membrane works? It will evoke an action potentials, it will repolarize the whole ventricle, and after the whole ventricle will repolarize. During the repolarization, which is in case of the heart is quite long, 1 second, during repolarization, no other action potential can appear because everything is depolarized and inactivated. In the re-entry mechanism, this membrane behavior changes and absolutely different situation develops. You can imagine that there is a funny shape of the structure. For example, there is a certain possibility to go to an action potential to go around because it is connective tissue and it is excitable muscle cell. In normal cases, what happens? One action potential appears at the input and will leave in most outputs. The action potential which is going around cannot go back to here because the whole area is depolarized and it cannot, the action potential cannot propagate and will stop here. Therefore, the ratio between the action potentials here and here is the same. No pathologic circumstances. But sometimes this part can be anoxic, hypoxic area, or the water supply, blood supply is not proper. And therefore, there are modifications here. It means that there is a unidirectional block and there is a slow conduction of the action potential. In this case, it can occur that the action potential which is going around will enter into this ill area and very slowly can propagate only through this area. The action potentials arriving here cannot cross because there is a unidirectional block, but no block is in this direction. Therefore, in this situation, the action potential which arrives here, a little bit slowly, can arrive here, can re-enter again the whole system, because the membrane here is already repolarized and can be activated again by this extra action potential. So this is the name of the mechanism is re-entry, that the action potential can enter again to where before could not enter because it was depolarized. But because the membrane had enough time to repolarize, the extra action potential can reach and can be that extra action potential. Now, it was a very interesting discovery. The cardiologist discovered different anti-arrhythmic drugs. These anti-arrhythmic drugs were very important to protect the human heart from the development of extra systolic or fibrillation. These anti-arrhythmic drugs, you can imagine easily, depress the activity of the membrane. For example, by blocking the sodium channels, which means that the action potential will develop slower, the sympathetic tone which would stimulate the heart reaches the activity, or there are drugs which are able to slow down the repolarization, to extend the repolarizing period, which protect the heart from the new action potential. For there are drugs which are able to block the calcium channels also, the voltage-dependent calcium channels. Therefore, for example, the pacemaker activity would be smaller, slower. And finally, there are special drugs which can decrease the heart rate, can cause bradycardia. So the discovery of the different antiarrhythmic drugs which try to decrease the activity, the excitation of the cardiac membrane at different points were very useful, and they could prevent the extrasystolic fibrillation. But later, more and more publications reported that using the antiarrhythmic drugs, they realized that the extrasystolic fibrillation appears more frequently. Therefore, the antiarrhythmic drugs had a pro-arrhythmic effect. So they did the opposite, which was expected. And they tried to study what can be in the background. And they realized that this re-entry mechanism can cause this pro-arrhythmic effect, because the anti-arrhythmic drugs can decrease the excitability of such an area, which makes that there is a blood and there is a much slower crossing around this area for the action potential, and the action potential then enters again here. This membrane will be depolarized and the second action potential can be generated. So they found that some anti-arrhythmic drugs in different situations can have a pro-arrhythmic effect. Therefore, it's very important in the medical treatment to decide exactly how high concentration of the drug is useful and what kind of anti-arrhythmic drugs has the best result. It has some anti-character of these things. Okay, now after the pacemaker action potentials, we have to continue with the second group of the normal action potentials, which can be recorded by the muscle fibers, so the working muscle fibers. And this is a characteristic action potential recorded at the ventricular fiber. I would like to mention that this is the time scale, several hundred milliseconds. Do you remember? On skeletal muscle, an action potential lasts about 1, 2, 3 milliseconds, very fast. Or in the neuronal structure, the action potentials are very fast. But here, in the heart, cardiac membrane, there is a long-lasting action potential. Long-lasting, it means that it lasts for several hundred milliseconds. And this long-lasting duration is the explanation, partially, that why the heart rate is only 60, 70, because this is very, very long. How can we explain the different parts of this fast action potential? How can we explain? The explanation is that the fast starting phase, because these are fast action potential, is due to the opening of voltage-dependent sodium channels. These are fast channels, very quick opening. The sodium enters, it depolarizes the membrane. The larger depolarization will produce larger, the opening of more sodium channels, entering more sodium ions and bigger depolarization. This is the so-called Hodgkin cycle. Okay. So it's quite clear that the sodium channels open and the membrane is depolarized very quickly. This line, this curve, indicates the extent of sodium conductance. How many sodium channels are open? It's quite clear that if we repolarize the membrane, more and more sodium channels will open, then they will inactivate and the sodium conductance will decrease again. Therefore, this transient increase in sodium conductance, the transient opening of sodium channels, is necessary to decrease the membrane potential to a lower value. What maintains the depolarization, the long-lasting depolarization? The fact that this initial depolarization will open not only the sodium channels, but the slower calcium channels. The opening of calcium channels will make possible the entering of calcium ions, positive charges, and will maintain the depolarization. But because the calcium channels are slower, and at the same time, the potassium conductances start to increase, therefore, there is a transient period which is a slow repolarization, and during this period, the calcium channels are open, and the potassium channels are open also. This one will depolarize the membrane, maintain the depolarization. The potassium and chloride channels try to repolarize the membrane, and the balance between them will result in a slow depolarization period, which is called plateau phase. Plateau phase, long-lasting depolarization. So, and the last period is the fast repolarization, then the calcium channels will close, and the open potassium channels will repolarize the membrane completely. Therefore, the repolarization on the ventricular muscle fibers has two different periods. The first one is the slow depolarization, which is called plateau phase, and then the faster repolarization, which restores the normal membrane potential. I just would like to emphasize again the same initial depolarization opens the sodium channels, the activation rate will inactivate the sodium channels. The same depolarization opens the calcium and the potassium channels. And the difference in the kinetics for different channels results in these action potentials. Now, there is an interesting question. How can we explain the frequency dependence of action potential? Because we can evoke action potential in maybe 20 to 30 times over a minute, but we are able to evoke action potentials from the cardiac membrane more than 150 times during a minute. If the plateau phase lasts for several hundred milliseconds, how it is possible to speed up the action potential repolarization, how it is possible to decrease the duration of the action potentials. You can see here in the superimposed record that if the frequency is higher and higher, the fast repolarization starts earlier and will repolarize the membrane earlier, and the next action potential will appear, will be generated much earlier. Therefore, the frequency can be quite high. How can we explain this one? Now we explain this with the special behavior of the potassium channels. The potassium channels are slow channels. If the repolarization is fast, there is no time for all the potassium channels to be closed, but some of them remains open, and the next action potential is evoked. In this case, at this point, a lot of potassium channels are open already and starts to repolarization much earlier than in normal case. Here the time is long enough, all the potassium channels can close, and all of them has to be open again with a new repolarization. But if the frequency is high, there is not enough time to close the potassium channels. Some of them will remain open, and they can start earlier the fast repolarization. It's very important because many times during sympathetic stimulation in other cases, the heart rate can be maybe 180 or at least or something like that. So it's an important mechanism. Okay, now we have to speak about an important phenomenon. This important phenomenon is the refractory period. The refractory period is very important in the normal functioning of the human heart. What is the situation? If we evoke an action potential, the plateau phase will develop and the membrane will repolarize again. If we try to investigate how the excitability of this membrane changes during an action potential, how can we do it? We can do it by evoking two electric stimulus. The first stimulus is to evoke the first action potential, and after we can apply the second stimulus after different periods of the first one, and we can see that whether the second stimulus will be effective, can evoke a second action potential. Now, finally, we can measure that increasing the length, duration of time between the two stimulus, the probability to evoke a second action potential will be larger and larger. Therefore, a certain period during the first action potential is absolutely inexcitable. Using even infinite stimulus intensity, we cannot evoke a second action potential. What is the explanation of this absolute inexcitability, which is called absolute refractory period? It means that during this shaded area, you cannot evoke second action potential. The explanation is that the membrane is depolarized, not yet repolarized. The depolarized membrane, the sodium channels are in inactivated state and cannot open again only if the normal membrane potential brings back these channels into the closed state, into the resting state. The inactivated channel cannot open again. We discussed the sodium channel. So, how long the plateau phase is maintained? The membrane is depolarized, the sodium channels are inactivated, and cannot open again. We have to repolarize the membrane more to put back the sodium channels into the resting state, and in this case the second stimulus can evoke a second action potential. Okay. After this absolute refractive period, there is another period which is called relative refractive period, where it is possible to evoke action potentials, and we need much higher stimulus intensity. What is the explanation? It means that with progressive depolarization, more and more sodium channels can go back to the resting state and can open again. But at the beginning, only a few sodium channels will go back to the resting state and can open again. In this case, we need a higher electric current to open these channels. Why? Because these resting sodium channels are located very rarely. The density is very low. Therefore, we need a larger current intensity to be able to reach the threshold value everywhere in the membrane to evoke a propagated action potential. Very interesting, you see. First, so-called abortive action potentials appear. The shape is not normal, because there is no enough sodium channel to develop the fast plasma phase. Case of time, here it's quite clear that the majority, the large majority of the sodium channels are in resting position and normal action potential can be used. So, and finally, this figure doesn't indicate, but I mentioned that after the action potential, different so-called active potentials, hyperpolarizing or depolarizing after potentials can occur, because the closure of all the potassium channels do not coincide in time exactly with the repolarized state. Therefore, the open potassium channels can hyperpolarize with the channel, or the repolarization is slower there for a repolarizing action of the potential can occur. Okay, how can we summarize this information? The first statement is that the excitability of the membrane, the ability to open the sodium channel again, is voltage dependent. It depends on the membrane potential. If the membrane is depolarized, the membrane is inexcitable, the sodium channels are inactivated, they cannot open again. If we repolarize the membrane excitability will appear again. And this is the reason why we can say that the excitability is voltage-dependent process. And why is it so important? It means very important because during the cardiac action potential, during a certain point of repolarization, the membrane is inexcitable, and no second action potential can appear. So, the cardiac membrane is protected by the depolarization from a second stimulus, is protected from the extrasystoles or the fibrillation, because a certain time has to spend after the first action potential to be able to accept the second stimulus and to appear on the second one. Therefore, this protection of the heart muscle is a very important thing. I should shortly mention that the pacemaker cells, the calcium channels are more lazier. So in this case, the intracranial periods are longer. What does it mean? There are pacemaker cells at the AV node. Therefore, crossing of the action potentials through the AV node is a very slow process. Very slow process because the action potentials which arrive to the edge of the AV node will evoke pacemaker action potential, slow response, and this system has a longer refractive period and it takes some time to cross the AV node than the normal action potential would be able to cross. Okay, we have to speak about this protection. What does it mean? That the long-lasting action potential of the heart protects the cardiac membrane, protect the second stimulus. We can compare the behavior of the skeletal muscle fibers and the behavior of the heart muscle. What happens on the skeletal muscle? Do you remember? The action potentials of the skeletal muscles are very fast. 2-3 milliseconds is enough for the complete time course. What is the role of an action potential? It will reach the calcium channels of the SR membrane, as you heard, and the whole activation of the contractile response originated. Therefore, a single action potential sends into the cell a package which opens the calcium channels and the contractile response develops. But the refractory period in this membrane is very short, and the tape tubus and so on has a very short refractory period. Therefore, if you evoke a second action potential, for example, 10 milliseconds after the first one, the second action potential can propagate into the fiber, can send in the message, can open new calcium channels, and the contractile response can develop even the first response is not over. This is a superimposed contractile response, which is possible because the two action potentials evoke its own own contractile response independently from the other one. Therefore, if it is superimposed, it's possible. What happens if the evoke 10 action potentials after the nerve? It will be the tetanic response. All of them evoke the calcium release, and there will be a long-lasting tetanic response. Now, what is the difference to this one and the heart muscle? The heart action potential lasts several hundred milliseconds. The action potential open the calcium channels on the surface membrane, the calcium enter, calcium will be released from the side, we will discuss it later. But the majority of the contractile response, the large part, is over during the plateau phase. And because this plateau phase protects the cardiac membrane from a second stimulus, from a second action potential, until the time when the contractile response is not over, no second activation can occur. Only this second action potential, which now in the relative refractory period, in the normal period, is effective, only this at this time can evoke a second action potential. And the contractile response is not a superimposed record, it's an extra systole and cannot sound. What does it mean? In normal circumstances, the heart muscle cannot be tetanized. Cannot be tetanized because the refractive period is too long and do not allow the very fast repetition of contractile activation. It takes some time and the second one is done. So, why is so important? It's very important because if an action potential appears from the heart, it will depolarize the whole heart. And the whole heart, all the cells, will contribute in the contractile response. It will be the systole of the ventricle. And for this proper systole, it is necessary at the same time, the same type of contraction at all the fibers. And the simultaneous response is protected by the long refractory period. This long-lasting, very well organized response is necessary for the pump activity. Pumping means the 70 milliliter of blood has to eject towards the aorta. And the ejection of 70 milliliter takes some time. Therefore, it's very important for the normal pumping activity, very important to protect the ventricle from a second contractile response, because it is necessary to eject the whole amount of blood and has to make possible the relaxation for the normal feeling that from the ventricle, the 70 milliliter blood will flow from the ventricle and the second injection is possible. So, therefore, this long-lasting refractive period limits the frequency. How many action potentials can be evoked during a minute, for example? This frequency limitation is very important in protection of the heart, the ventricular function. Okay, now we discuss the most important features of acyclic action potentials and the action potentials of the working muscle fibers. Now, next topic is to discuss how the excitation spreads from the assay node around the conducting system and is able to depolarize the whole heart. This conducting system is a very complicated system. The first step is the assay node, where the acyclic action potentials are generated. How the excitation can spread on the heart? Between the cardiac muscle fibers, there are gap junctions. These gap junctions have low resistance, so they don't prevent the action potential propagation from one cell to the other cell. Therefore, the heart behaves as a syncytium. If you evoke action potential at a point, it can reach all the muscles, all the muscle fibers, and can depolarize the whole ventricle or the whole heart. And this is made possible by the gap junction. The gap junction between two cells has roughly the same resistance than the intracellular resistance, therefore it doesn't prevent the propagation of action potential. Okay, this gap junction can change in certain pathological situations. The gap junction can be higher. For example, if the intracellular calcium is higher, concentration is higher. If there is a hypoxic milieu, the oxygen supply is not properly for the acid metabolic products is accumulated, or there are mechanical damages. Okay, if the resistance of the ganglion junction increases, the proper propagation is prevented, and therefore different changes, abnormal alterations can occur in the heart, and this will be the special systolic circulation. Okay, so the gap junction makes possible the smooth propagation of action potentials. But there is another system which makes sure that the propagation will reach all the fibers. And this system can be characterized by the propagation speed of the action potential into different areas. The SA node has a low propagation speed. It makes the pacemaker action potential appears in a certain point of the SA node. There is enough time for all the cells in the SA node to develop the pacemaker action potential. Therefore, a very powerful pacemaker action potential will reach the atrial muscle fibers and will propagate through the atrium. The propagation of the atrial muscle fibers is basically a very fast process. This is the situation that all the atrial muscle fibers will be depolarized, and the action potential depolarizing all the atrial muscle fibers will reach the AV node. Okay, it's very important. The propagation speed in the AV node is very slow. We told that these are pacemaker cells, slow responses, and long-lasting refractory periods. Therefore, this is a nodal delay. It means that the very quickly arriving action potentials will slow down before start to depolarize the ventricle. What is the advantage of this slowing down? The advantage is that there is enough time to depolarize all the ventricular muscle fibers, and there is enough time for the proper atrial contraction, for the proper atrial systole, because the action potentials are waiting in the AV node. This is the nodal delay. And after they reach the Purkinje fibers, and through the Purkinje fibers, they very fast reach the whole ventricle, and the ventricular muscle fibers has also a high conduction velocity, and this depolarization will depolarize the whole ventricle, all the muscle fibers in the ventricle. But it's very interesting that there is a certain regularity how the ventricular muscle fibers are depolarized. They are not depolarized at the same time everywhere. We can differentiate the depolarization of the endocardial part, you see, and the endocardial surface, these muscle fibers are already depolarized, then the epicardial part has normal membrane potential. And you can see that after the depolarization will reach the sub-epicardial part, and everything is depolarized, and now the repolarization starts. But very interesting that the sub-epicardial part will depolarize earlier. And it means that the subendocardial parts depolarize earlier and repolarize later. So the sub-epicardial parts subendocardial parts will be depolarized for a longer time than the epicardial part. Now, this asynchronous depolarization is very important to understand the ECG record and the different parts. Okay, we listed the different advantages of this AV nodal delay. This nodal delay makes possible the separate atrial and ventricular excitation. First, the atrium is depolarized, there is the atrial systole, the blood can flow into the ventricle, and during this time, the ventricular fibers are not depolarized due to the delay. And after the action potential reach the ventricular muscle fiber, the ventricular fibers contract, the ventricular systole develops, but from this time, the blood cannot flow further to the ventricle, but the ejection begins towards the large arteries. Therefore, the atrial ejection and the ventricular filling is happening at the same time as possible. There is a frequency filtering at the AV node. It's a very important thing. There is a very serious practical significance. Sometimes the atrial muscle fibers fibrillate. It means 200, 300 action potentials are appearing in the atrial muscle fibers. What happens with the contraction relaxation cycle? It is impossible because the repolarization frequency is so high that the atrial muscle fiber cannot follow it. What does it mean? The ventricular cannot contract, just fibrillate. Very fast contraction, relaxation, but no pumping activity. It means that the atrium, in this case, became part of the large veins. Doesn't do anything, just allow the blood to flow through. Now, what is the significance of the AV node in lucky cases? The AV node has a frequency filtering ability and will not allow more action potentials, just 70 in a minute. Filter the high frequency and do not allow the remaining 250 or 300 action potentials. Why? Because the refractive period of the AV node is very long lasting and the refractivity do not allow the crossing of no action potentials. Therefore, the atrium will fibrillate with a frequency of 300 over a minute, and the ventricular muscle fibers will contract only 7 times in a minute, because the AV node protects them from the high frequency of action potentials. Therefore, the ventricle can maintain the pumping activity because the ventricle has enough time to fill up and has enough time to eject the blood towards the periphery. What happens when fibrillation occurs at the ventricular fiber? Means that the pumping activity collapses, is not able to maintain the circulation, the blood pressure goes down, the circulation stops, and the patient will die if nothing else happens. very important. Now, there is another side of the question. What happens if the AV node is completely blocked? Do not allow the action potentials to cross. It means that the ventricular muscle fibers do not get impulses, do not get action potentials, and cannot contract. It means if a complete block of the AV node conduction is lost, in this case, the ventricle will stop, and the pumping activity is ended. But in many cases, it doesn't cause the death of the patient because the AV node as a secondary pacemaker, subordinated pacemaker, starts to evoke action potentials in his own rate, the 40 over a minute, and can maintain the pumping activity of the heart. It's very important. Something the patient doesn't feel that the atrium fibrillates. Because basically, the pumping, the ending of the pumping activity of the atrium doesn't modify too much the feeling of the ventricle. And sometimes only the medical examination can figure out that this is a fibrillating atrium and the heart is, and the ventricle is working at normal frequency. What is the danger in this case? If the atrium doesn't contract, the blood is just staying in the atrium, and the flow is not fast enough. In this case, the blood will coagulate, and thrombosis and embolysis can develop. Therefore, it's very important to discover that the atrium is fibrillating because we have to apply the different drugs to prevent the blood coagulation. The next advantage of this nodal delay that because the refractory period is long-lasting, the action potentials cannot go back to the atrium. Why is so important? If there is a normal action potential in the atrium and the second action potential somehow develops, the extra systole can propagate into the ventricle and will cause a ventricular extrasystole also. But this extrasystole and the extra action potential cannot go back, cannot propagate back to the atrium because the AV node rectifying the system. Therefore, if this rectification wouldn't exist, the action potential from atrium to the ventricle back and again ventricle can cause fibrillation through the AV node. Now it is prevented by the long-lasting refractory period. And this nodal delay results in that all portions of the ventricular muscle, because they have enough time, and here the propagation is very fast. Basically, all the muscle fibers in the atrium they will contact at the same time. 80% the proper ejection of the blood. I mentioned when we first spoke about the fibrillation that there are two different frequencies we can speak about atrial flutter. The flutter means that the frequency is 220, 350. In this case, the ECG record is full of T waves because the frequency is not too high. But if the frequency is higher, about 350, even 600 over a minute can be. It is the real fibrillation. The real fibrillation means that we do not see any T wave, because this is the QRS complex and this is the T wave. But the T wave, which indicates the electric depolarization of atrium, disappears. Just a fibrillating baseline shows that 300, 600 action potentials running through the whole system. Now, this show you that it is called ventricular arrhythmia. Why? Because the AV nodes protect the ventricular fibers, but it is very accidental that each action potential can cross the AV node. Therefore, the ventricular functioning will be arrhythmic and the relationship with the action potentials changing. Now, if the flutter or the ventricular fibrillation reach the ventricle, in this case, the circulation stops, and you can see a normal ECG called normal blood pressure value, but we induce fibrillation by electric stimulation in an experimental animal. The ventricular fibrillation disappears and the blood pressure goes down. And the other possibility is the defibrillation. When we apply larger current pulse, and this large current pulse can depolarize at the same time all the fibers. And therefore there is a nice possibility to return back to the normal ECG, normal electric activity, and the normal blood pressure value. This is the reason that many times the ventricular fibrillation can be cured by the strong current pulse as a part of the resuscitation of the heart which stops. Okay, these were the information today. Thank you very much.